Um, we've seen a lot of these problems where it says estimate f prime or estimate a value. A lot of times it's with slope. So we start off with slope. With part B, it says evaluate the definite integral. So definite integral. Think of this as two separate problems. One we can handle using power rule, and the other one we can handle using first theorem, meaning that we know the integral of f prime will turn into f of b minus f of a. Right, so 3 becomes 3x, and then we plug in the upper and lower bound. F prime becomes f of x, and then we plug in the upper and lower bound, f of b minus f of a. And then we can replace these with values from the table. And then we can just really think that two separate problems. One is the result of power rule. The other is result of first theorem. We add those results together. One gives us 33. The other gives negative 25. And then positive 8 is our answer. For part C, we're going through left Riemann sum. So width times height for each of our 4 rectangles. And that totals up to be 18. For part D, what they're trying to get us to do is they mentioned line tangent and line secant to the graph. So we do know that they give us, suppose, okay, they tell us that the graph is concave down for all and for all the values between 5 and 8. So that gives us a hint in terms of what the graph looks like. So this is what they're trying to get us to do for part D, is they're indicating that the graph is concave down. Okay. And they're trying to say, what is the relationship between a line that is secant to the graph versus a line that is tangent to the graph? So secant just means a line that goes through 2 points. Tangent is a line that goes through 1 point. So the whole point is that if the graph is concave down, then anything that is secant is going to under approximate a point on the curve, right? Anything that is part of a secant line is going to sit below the actual point on the curve. So we're going to get an under approximation from a secant line. Right, because we know that this point is going to be lower than any point on the curve. Meanwhile, you're going to get, if it's a tangent line will over approximate a point on the curve. So that's what they're trying to do. For part D, we're given information where we can find points on a graph, find a slope, pick one of the points, do point slope form, and then we plug in a value to estimate the approximation. And we know that because of the shape of the graph, this point is going to be lower than the actual point on the graph. Meanwhile, tangent, we're given slope, we're given order pair, we build that tangent line, we plug in the decimal value. That decimal value is going to be clearly above the curve. And then in a related problem, let's say we had a graph that's concave up. If a graph is concave up, then a secant line, again, a secant line is just a line that goes through 2 points on the curve, is now going to be over approximating anything on the curve. And a tangent line will therefore under approximate, right? Everything is opposite here. So if I'm trying to compare this point with this point, with this point, this is over approximating. This is the actual value, and this will be under approximating. So for the tangent line, we take our order pair, we take our slope, we do point slope form, and then we plug in this case, it's not decimal value, it's 7. So we plug in 7, and we get 4. And we know that 4 is going to be clearly greater than the actual value on the curve. So that's the conclusion that we can make. Now, secant line will sit below the curve. So they gave us 2 points. We find the slope between those 2 points. We use point slope form, build our tangent line. We plug in 7. We get a number that's 4/3. And we know that, let's say this is 4/3. 4/3 is going to be less than the actual value on the curve. Okay, page 6. Okay, Ben rides a bicycle back and forth along a straight east-west track. This twice differentiable function V models Ben's position on the track measured in meters from the western end of the track at time t, measured in seconds from the start of the ride. The table gives values for B of t and Ben's velocity measured in meters per second at selected times t. Part A, use the data and the table to approximate Ben's acceleration at time t equals 5 seconds. So acceleration, we know, is the slope of velocity, so we can just go through our slope formula. Right? Change in velocity over change in time will give us meters per second squared. Part B, using correct units, interpret the meaning of the definite integral of the absolute value of V of t. We saw this yesterday as well. We know this is total distance. And it says use left Riemann sum to approximate. Okay, so width times height, left Riemann sum from 0 to 60. So we can use our subintervals here, 10, 30, 20. And then we multiply with our velocity. So 10 times 2, 30 times 2.3, and then 20 times 2.5. Between 40 and 60, must there be a time when Ben's velocity is 2 meters per second? So if we look at 40 and 60, we can see that, I mean, we see a velocity of 2 meters here. IVT is not going to be good for this one, right? Because 2.5 to 4.6, we don't see 2 landing between those two numbers. Sorry. My bad. I wasn't showing all the work I was doing before. Okay, so part C. Between 40 and 60, we see that velocity is clearly not, we can't guarantee that there is going to be a 2.0 because between 2.5 and 4.6, it's not going to cross paths with 2. So we can't rely on IVT if we want to guarantee a velocity of 2. However, maybe we can rely on our position. We know that the slope of position is velocity. So maybe an average rate of change will give us 2 meters per second. If it does, then we can guarantee there must be a 2 somewhere, a velocity of 2 somewhere between here. So that's using mean value theorem, where we can't guarantee the value on our table, but we can use the table above it and do the slope of that table and then use that information to guarantee a value at this level. So we can pick those 2 points between 60 and 40. We can do change in meters over the change in time. So 49 minus 60 divided by 4 minus 9. Sorry, 49 minus 9 divided by 60 minus 40. And that gives us 40 over 20, which is 2 meters per second. So therefore, there must exist a t and the value from 40 to 60 such that v of t is equal to 2. Okay, part D. A light directly above the western end of the track. A light is directly above the western track. Then writes so that at time t, the distance L is satisfied by LT squared equals 12 squared plus B of t squared. At what rate is the distance between the light Ben and the light changing at time t equals 40? So anytime we see the word rate, we know that we have to involve derivative. So let's see if we can build a derivative. But the fact that we have L of t quantity squared, that's indicating to us we got to go through a chain rule here. So that extra bracket indicating we got to go through a chain rule to build a derivative. So there's an outside, inside derivative we got to go through. So outside's derivative is that bracket squared. So we get 2 bracket to the first power times inside's derivative. That becomes L prime of t, right? Equals 12 squared is a constant. That constant goes to 0. And then another chain rule with B of t squared. So we get 2 bracket to the first power times B prime. Okay, so this is what we need to do. We have to figure out at what rate is the distance between the bend and the light changing. So we're looking for L prime of 40. Okay, that's our goal, L prime of 40. But let's go ahead and fill in all the t's with 40 because that's where t is. So we're going to go ahead and make our substitutions and see if we can fill in the rest of the values after we do that. So I can say 2 times L of 40 times L prime of 40 is equal to 2 times B of 40 times B prime of 40. So L of 40 requires us to kind of go back to our original equation and plug in because L of 40 is based off of this original equation. So L of 40 squared is equal to 12 squared plus B of t squared. And B of 40 is 9. 9 squared is 81. So we get 144 plus 81 is 225. And we know the square root of 225 is 15. Okay, so now we'll take that and put it in and see if we can solve for L prime. B of 40, we can pull that from our table. B prime of 40, we can also pull that from our table as well. So B of 40 is 9. B prime of 40 is 2.5. Take those values, divide it. So 2 times 9 times 2.5 divided by 30. And we get 1.5 meters per second. Okay, I'd like for us to work through some antiderivative word problems. So if we can turn to page 9 in your packet. Okay, this is a calculator active problem here. A water tank at Camp Newton holds 1,200 gallons of water at time t equals 0. During the time interval between 0 and 18 hours, water is pumped into the tank at a rate of W of t. And then at the same time, water is being removed at another rate, 275 sine squared t over 3. Is the amount of water in the tank increasing at t equals 15? So we can just plug 15 in for both and see which one is higher, right? Whichever has a higher rate is going to indicate what's happening to that water level, right? If WT is greater than R of T, then water level will be rising. If the R of T is greater than W of T, then water level is going to be falling. The first challenge is to figure out how to put this in the calculator because we can't put that squared where it is indicated. So what does that squared mean? Or how would you put this in the calculator knowing that you can't do sine squared of t over 6? Yeah, exactly. Yeah, so you have to literally put that squared outside a set of brackets. So the way that you're going to put it in the calculator will look like this. 95 square root of x, parentheses, sine of x over 6, parentheses squared. So that's one of the challenges here, just knowing how to even put it in the calculator. So I would put that under y1, and under y2, 275 parentheses, sine of parentheses x over 3, parentheses squared. So we can plug 15 in for W of t. We can also plug 15 into R of t, and we just simply see which one is higher, right? For part A, I'll say W of 15 minus R of 15 and see what that gives me. If I get a positive value, I know W of 15 is going to win out. It's going to have the higher value. My rate is increasing. But if R of 15 is greater, then I know that my R of 15 is now going to have a higher value. So I'm just really really looking to see if which one is greater. So let me put this in here. So 95 root x parentheses sine of x over 6 parentheses squared. Yeah, and then we should be in radian mode, never in degree mode, always in radian mode for the entire test, entire AP exams. Okay, so I'm going to my home screen. I'm doing alpha trace y1, which is holding my W of t. I'll put 15 in, minus alpha trace y2, parentheses 15. I get negative 121. So we know negative 121 is less than 0. That means R15 is going to have the greater rate. I know my water, the amount of water is going to be decreasing and not increasing. to the nearest whole number, how many gallons of water are in the tank at time t equals 18? So whenever you have this rate in and rate out, you're always going to go through this bit of a formula, and that formula looks like this. Anytime I'm looking for a total amount or any final amount, it's equal to the initial plus the amount added minus the amount removed. That way we can keep track of all these moving parts here. And if we take all three things into account, we're going to know how much there is at any moment in time. So how much is there to begin with, how much has been added, and then versus how much has been removed. So I'm going to create a original formula. A of t is any amount at any moment in time. We know that we have 1,200 gallons to begin with, plus the amount added, so from 0 to t of w of x dx, minus the integral from 0 to t of r of x dx. So we know that the integral of w will give us the accumulation of our rate, or everything will be in terms of gallons now. So this is initial amount gallons, initial amount of gallons added, and then amount of gallons removed. Okay, so that's the general formula, but I know what I want is how many gallons at the 18th hour. So I'll do A of 18. Okay, so in our calculator, put this in here. So I'll do math 9 from 0 to 18. I have y1 holding my w. So alpha trace y1 dx 2695. And I'm also doing math 9 y2 from 0 to 18 as well. This is how much I want to remove, 2585. Add those together. I got around 1310 gallons. Part C, at what time is the amount of water in the tank at an absolute minimum? So anytime I see the word absolute minimum or minimum maximum, I know I'm going to be involving EVT, extreme value theorem, which means I'll test endpoints and critical points. Endpoints are easy to find. We know 0 and 18 are, we already have one of them. But critical points comes from the derivative. So let's build a prime. So to find critical points, we're going to set a prime equal to 0. So let's build A prime first. So A prime is the derivative of this equation. 1200 goes to 0. The derivative of this integral will just become w of x, right? We're stripping away the integral and just holding on to that w, putting in that t there. And same thing here, derivative of this will wipe out the integral. I'm just left with r of t. So I'll set a prime equals 0. So I'm trying to figure out when is a prime, or when is w of t minus r of t equal to 0. So this we don't want to. We'll take advantage of our calculator. So the way we do that is we're going to graph this equation and then look for the x-intercept. So to graph it, I'm going to go to y3 and then just say y1 minus y2. Because that's basically my wt minus rt. So y1 minus y2. I don't want to have to see all my graphs, so I'm going to go to that equal sign under y2 and y1, hit enter, so I can unhighlight those equal signs, so that the only thing that I'm seeing is that y1 minus y2. Okay, zoom 6. I think that it's going to be really hard for me to see the graph. One reason is, yeah, you see when you have a straight line like that, that means you're zoomed out way too. You're zoomed in too much. So I'm going to go to window. I'm going to adjust my window here. One thing I noticed is that my t value is between 0 and 18. So I'm just going to let my x min, x max be like 0 and 20, just so I don't have to look at more than I need to. And then here, if you look, your coefficients are 95, 275. Those are in the hundreds, or mostly in the hundreds. So I would just say, let's say negative like 300 to 300. So we can kind of see, these coefficients kind of gives you an idea. You probably want to be in the hundreds to be able to see the graph more clearly. So I'll say like negative 300, 300. Maybe this is overkill. But remember, you're only playing with those 4 numbers. You just want to set it so that you can have something where the graph has some curve in it. You can actually trace it. Let's see if that's too much. Let me see, did I? Okay, so I'm seeing 2 critical points here. One is here, one is here. This one is too far out. This one doesn't hit. So if I do second trace 0 on my first x-intercept, I'll pick points on both sides. I get 6.495. That's one of them. Second trace 0. Hit enter. Hit enter again. And I get 12.975. So I'm going to take each of them and put it into A of t. So my critical points, t is equal to 6.495, and t is equal to 12.975. So now each of them gets inserted into my A of t equation. So I need to find A of 0. Well, A of 0 is easy. We already have that. That's 1200. We also have A of 18. That's 1310. We should have to worry about A of 6.495 and A of 12.975. And we're just following this formula here, replacing my upper bound with 6.495, both of these. That should get us to 525. We do the same thing for the 12th hour, the other critical point. $16.97. So we're looking for absolute minimum. So we want to find the lowest of these values here, and we see the lowest is 525, right? So absolute minimum is at the 6.49 fifth hour. So absolute minimum is 525 gallons. For T is greater than 18 hours, no water is pumped into the tank, but water continues to be removed at R of T until the tank becomes empty. Let K be the time when the tank becomes empty. Write but do not evaluate an equation involving integral expression that can be used to find the value of K. So we just have to set it up. No need to solve it. So here we can say, okay, we know that at 18 hours, there's going to be 1,300 gallons. And after that, no more water gets pumped into the tank. But now we're just looking at the removal rate to see, okay, the removal process is still ongoing until all this water drains. So we want to create an equation to figure out how long will it take for all this water to drain out of the tank. So we can say integral, we just focus our attention now on R of T since W of T is no longer involved. So we'll say from 18 hours until the kth hour, we're going to keep running this R of T until we reach 1310. Because that's how long it's going to take, however long it's going to take for all 1310 gallons to get drained out by R of T. That's all we need to do, just set up that equation. All right, number 10, page 10. There's no snow on Janet's driveway when snow begins to fall at midnight. From midnight to 9 a.m., snow accumulates on the driveway at a rate modeled by F of T. F of T equals 7t e to the cosine of t cubic feet per hour, which is measured in hours since midnight. Janet starts to remove snow at 6 a.m. The rate of G of T represents the rate at which Janet removes snow from the driveway. So we see that G of T represents her rate in terms of the work that she does. So between 12 a.m. and 6, she's inside the house. She's not shoveling snow. But then between 6 and 7 a.m., she's working at a rate of 125 cubic feet per hour. So she's working at a pretty good clip here. But then between 7 and 9 hours, she's working at a slower rate of 108. Still making progress, but not as fast as she was for the first hour. So 108 cubic feet per hour. So part A, so we have two things going on. We have snow that's falling, that's causing the amount of snow on the ground to accumulate. And then also we have Janet working, trying to get the snow off the ground. So part A, how much snow has accumulated on the driveway by 6 a.m.? Here, we just have to focus on f of t. We're not worried about what Janet's doing. So we're trying to figure out how much snow is going to accumulate in the 6 hours after midnight. So just have to rely on f of t. We know we're trying to get from cubic feet per hour up to cubic feet. So we got to take the integral. So part A is just the integral from 0 to 6 of 7t e to the cosine of t dt. But then the calculator, math 9. Part B, find the rate of change of the volume of snow on the driveway at 8 a.m. So two things are happening at 8 a.m. One is Janet is trying to get the snow off the ground, but snow will keep falling. So we're trying to figure out, what is the rate of change of the amount of snow? Is snow getting still accumulating on the ground, or is it getting removed? So the rate of change of snow on the ground. We can look at two things, right? We can look at what the rate of snow that's being added to the ground, and then subtract the rate at which Janet is removing snow. And if f of 8 is greater than g of 8, we'll get a positive number. If we get a positive number, that means there's more snow being added to the ground than what Janet is able to remove. But if g of 8 is greater than f of 8, then we'll get a negative number. That means that will tell us the rate at which snow is getting removed off the ground. So plug 8 into f of t. And then g of 8, her rate is 108. And then we plug that in the calculator, 7 times 8 times e to the cosine of 8. Minus 108, we get negative 59.583 cubic feet per hour. So that means at the 8th hour, despite the fact that snow is still falling, Janet is making enough progress where she is causing almost 60 cubic feet per hour of snow to be removed off the ground at that 8th hour. So there's progress in terms of getting snow off the ground. Part C, let h of t represent the total amount of snow in cubic feet that Janet has removed. So this goes back to that formula that we've been working on. My final amount equals my initial plus amount added. Okay, so we're just focusing on the what Jen has removed. So it's just how much there is, and then subtracting subtracting her work. So this one we have to just adjust it where the total amount that she removed is going to be based off of her initial, how much snow there is to begin with, and then plus the amount removed. So this initial amount represents the initial amount that she's done up to that point. Okay, so I'll have you guys see if you can finish off the rest. And then part D is where you could go back to that formula that's more familiar. Total amount equals initial plus amount added minus amount removed. All right. So your homework, pages 6 through 12, this will be due Tuesday after break. So just give you a heads up, when we come back from break, we're going to work on this packet. Thursday quiz, and then the following Tuesday and Friday, we're going to have multiple choice test. And then we can start, continue our AP review. Encourage you guys to see if you can chip away at packet 6. Again, packet 6 is due May 9th for seniors. So see if you, even if you can do 1 page a day, that will make a huge difference. Okay, come get your phones. Let me know if you're needing packet 6 or if we don't have packet 6. Oh, sorry.
It's okay.
My bad. Thank you.
I'm rounding here, so I do the approximate equals or judge here.
You can do approximate. That's fine.